Good morning, friends. We'll start electromagnetic testing. So, electromagnetic testing technique offers several advantages over other methods. The ET method most often refers to magnetic flux linkage, MFL testing, eddy current testing, microwave testing. Although magnetic beacons and noise, ground penetrating radar, and others may fall within the category MFL, GPR, MW are considered separate methods, but all electromagnetic testing. Vectors. All ET techniques, as well as a variety of electromagnetic waves and fields that are encountered daily, are described by the set of parallel differential equations known as Maxwell's equation. These equations integrate electric, magnetic, and electromagnetic induction theories. An electromagnetic field is a vector quantity, which means that it has both magnitude and three-dimensional direction. Fields may be described by their rotation or curl and the nature of their source, that is divergence. The mathematics behind magnetic flux linkage and DC potential drop technique is based on elliptic partial differentiation equation with zero curl and zero divergence, meaning static magnetic field where the magnetic and electric fields are coupled. That is magnetic flux linkage. Quasi-static, the time-varying condition of eddy current such as remote field testing or multi-frequency eddy current testing are described by parabolic equation. When an electric field changes with very high frequency, there is another current within the specimen. It is known as displacement current. The displacement current is proportional to the frequency in the dielectric permittivity of the material. So test frequencies, each technique varies in the test frequencies. Magnetic flux linkage often uses test frequencies between 0 Hz to 60 Hz. Eddy current testing uses frequencies between 100 Hz to 10 MHz. Microwave testing employs test frequencies as 300 MHz. As described in Maxwell equation, the underlying physical process changes with test frequency. Electromagnetic fields with a frequency below 10 MHz said to be quasi-static, which means the displacement current is negligible. MFL use Hall effect sensors. Eddy current testing uses one or more coiled wire sensors, and microwave testing and ground penetrating radar use antennas. ET variables generally vary non-linearly with frequency. At times, the rate of change can vary from positive slope to negative slope because the complicated relationship between the variables. Most ET applications such as alloy sorting, heat treatment verification, hardness determination, thickness measurement require reference standards that properly match all changes that may exist in the test object. Equipment standardization with a proper reference standard is important to discontinuity detection. Electrical conductivity. Most metals are good conductor of electricity, and electrical conductivity of the test object is an important factor in many eddy current techniques. For simplicity, a change of conductivity is generally associated with a change in the ability of electrons to flow. Conductivity can be anisotropic and varies with several factors, including temperature, alloying element, and their concentrations, lattice structure or strain, and the number and concentration of dislocation within the atomic lattice structure. While conductivity, inverse of resistivity, may be described as absolute terms in Siemens per meter, the relative international annealed copper standard percentage IS scale is often used. The relative scale used annealed or soft copper with sample temperature of 20 degrees centigrade as the basis of comparison, identifying this material as 100 degrees, 100% ISES. Other conductors are then attributed a value relative to annealed copper. An example of thermal process is annealing, which reduces dislocation density and consequently the number of obstacles to flow of conduction band electrons. Mechanical modification may be room temperature plastic deformation such as cold rolling, which increases atomic lattice strain and dislocation density and change the material's electrical resistivity. The conductivity of aluminum alloys is of particular interest in some industries. Aluminum alloys may be thermally and or mechanically processed using special recipes to include a desired strength, corrosion resistance, or other property. Each alloy and recipe combination temper produces a somewhat unique electrical conductivity. Therefore, it is useful for rapid estimation of material properties in aluminum and other non-paramagnetic material. To obtain information about simple sample and inspection might include different test frequencies, a variety of types of configuration or probes, multiple probe orientation or different procedures, materials damaged during processing or improperly treated can be detected and removed from production without incurring further processing costs. Time varying current applied across the test coil produced a magnetic field, that is AC field. And this changing magnetic field induces a time varying alternating current, that is the electromotive force in the near surface of the test object. EMF amplitude varies with the applied voltage and with the driving frequency. Electrical impedance may be described as how much electrical circuit opposes the passage of current and voltage is applied. Impedance of a test coil varies as the conductivity of a nearby material. Impedance is complex sum, referring to vector addition rather than simple algebraic addition. Electrical resistance, inductive reactance, and capacitive reactance. Similar to the concept of inertia, inductance is an electrical circuit's opposition to a changing current flow. Impedance. Electrical impedance is both magnitude and amplitude and phase. The phase relationship within an inductor coil stems from current due to the electrical resistance and current due to the inductive reactance occurring at different times. In fact, these two contributions are 90 degrees out of phase, with voltage leading the current. The voltage travels first, then current travels at 90-degree difference. Sorting based on conductivity, the response of test coil is balanced, nulled in air point Z in the figure. Then the coil is placed near the sample. Electrical balancing is accomplished with the bridge circuit, such as Wheatstone bridge. This electromagnetic field comprises of electrical current flowing in closed loops, referred to as eddy currents, within the test object and a resultant magnetic field that opposes the primary field in the test coil. Its opposition is described by Lenz's law. Eddy currents only flow in the near surface of the test object, phenomenon referred to as skin effect. and the depth of penetration into the thickness known as the skin effect. Therefore, the eddy current testing is limited to surface or near surface evaluation of material and products. Skin depth varies inversely with the test object conductivity, magnetic permeability, and test frequency, self-inductance. When the test coil is near a non-ferromagnetic specimen, the self-inductance of the coil decreases. A change in the coil inductance is accompanied by a change in its resistance. Both variables are monitored by the eddy current test equipment. For example, it may be possible to distinguish two samples made from the exact same material when the hardness and consequently the electrical conductivity vary. When the test coil is near a ferromagnetic conductive sample, the typical decrease of self-inductance and the coil due to eddy current loss described above, as well as hysteresis losses in the magnetic specimen, is countered by self-inductance increase caused by the large magnetic permeability of the specimen. So near a ferromagnetic, it will increase. Why? The permeability. Magnetic permeability effect dominates the test response, and consequently the overall test coil's self-inductance change is positive. So test coil impedance change is opposite for non-ferromagnetic and ferromagnetic samples. The eddy current signal deflection will be opposite directions. Detection of discontinuities. The detect of small changes in the impedance caused by discontinuities. The test coil is generally balanced while near the specimen in figure, a discontinuity causes a reduction in redistribution of the eddy currents within the specimen, and the resultant impedance is altered. The complex impedance plane display showing the resultant phasor, the example of change of response from Z1 to Z2. So when it is placed near a conductive non-ferromagnetic specimen, that is negative. So coil configuration, eddy current testing, you just test coil configuration, absolute or differential. Absolute eddy current probes consist of single test coils. A differential probe requires at least two coils. Probes may have combination of absolute and differential coils and may even contain an array of multiple coils. Absolute coils can, however, struggle to indicate small changes in coil impedance, and changes in the distance between coil and sample, referred to as lift-up, can result in non-relevant test indications. Differential eddy current probes consist of a pair of coils connected in opposition so that the net measured impedance or induced voltage is cancelled out when both coils experience identical conditions. Differential probes are sensitive to relative changes in specimen, and they are sensitive to, so ferromagnetic is opposite and is non-ferromagnetic. Test coil impedance obtained by this from other values decreased ferromagnetic materials or increased non-ferromagnetic materials. What is this? There's something wrong. Okay. Differential probes are sensitive to relative changes in the specimen, and their sensitivity to discontinuity is higher than that of absolute probes. Differential probes are fairly immune to lift-up signals as well as probable noise and unwanted signals that affect both coils. Alternating current and direct current potential drop techniques, ACPD and DCPD, respectively, may be used to determine the conductivity effective permeability of the metal. These techniques use probe with four aligned spring-landed pins which directly contact the metallic test surface at defined distance from each other. The outer two pins pass through electrical current through the specimen, while the voltage potential different drop is measured across the inner two pins. Crack sizing. The potential drop technique is excellent for crack sizing. A distinct discontinuity beneath the probe alters the electrical resistance of the material. As current is forced around and underneath it, the altered resistance lead to a change of voltage potential because of the skin effect. ACPD is useful for surface and near surface discontinuity, whereas DCPD has a deeper depth effect. Epoxies, paints, and other non-conductive surface coatings, as well as surface oxides, dirt, oil, and grease must be removed, or they will prevent the current from entering the material. To avoid errors, the surface must be free from moisture, remain at a uniform known temperature. We'll stop here.